Hey everybody, my name is Ian Molina, and I'll be talking to you guys about biofuel chemistry and how they are manufactured, how they've been approved upon, and how they compare to other fuels. So let's begin with the definition of a biofuel. A biofuel is any fuel from which energy is obtained through a process of biological carbon fixation. Remember that a biofuel is made from a living organism and has not gone through thousands of millions of years of geological changes, such as our fossil fuels. So we'll begin with biodiesel and diesel. So petroleum diesel is a product produced through the fractional distillation of crude oil. The product contains a mixture of hydrocarbon molecules that range in size from 8 to 21 carbon atoms. The petrodiesel molecule is a pure hydrocarbon containing only hydrogen and carbon atoms and no oxygen. In ideal conditions, with abundant oxygen, burning this molecule releases only CO2 and H2O. Of course, oxygen makes up only 21% of the gas in air, while the rest being a mixture of about 78% nitrogen and small amounts of other gases like methane, neon, helium, hydrogen, etc. Beyond that, many petroleum deposits are contaminated by hydrogen sulfide and other sulfur compounds. The result is that burning petrodiesel produces sulfur compounds like sulfuric acid, nitrogen compounds like nitric oxide, not acid, and other contaminants. In other words, the reaction is not ideal. In many ways, the biodiesel and petrodiesel molecules are similar. In fact, the only real difference is on the right side of the molecule where the biodiesel has two oxygen atoms compared to the petrodiesel molecule. These oxygen atoms are what make all the difference in biofuels like biodiesel when they are burned. And we're going to begin with why oxygen exists in biofuels. So biofuels are produced through a process known as transesterification. On a side note, I'm really bad at these words, or a few of these words, so I might mispronounce a lot of them, but transesterification, that's what we're going to go with. Anyway, in this process, fats and oils from living organisms are broken apart to yield very long molecules that contain oxygen. This is the way that most biodiesel is produced, and it yields a molecule with slightly different qualities than petrodiesel. In essence, you take a triglyceride. This is another one I have trouble with, triglyceride. But anyway, it's made of 3 fatty acids and a glycerol molecule. And you react that with methanol. This yields a mixture of fatty acid esters that can be used as biodiesels, as well as glycerin molecule that can be removed from use for use in chemical applications, food processing, and other settings. So now we'll be moving on to the difference between biodiesel and petrodiesel. Really, oxygen makes all the difference in these molecules. Biodiesel provides a better knock protection, or a cetane number, I believe that's how you pronounce it, but a low energy density than petrodiesel. It provides less sulfur emissions, but more nitric oxide emission. Biodiesel freezes at warmer temperatures and is less stable during long-term storage, but it does provide better lubrication than standard diesel. Every single one of these differences is the result of the addition of the ester group to the long chains of hydrogen and carbons. Beyond changes in physical properties, biodiesel offers differences in chemical properties as well. First of all, the extra oxygen already contained in the molecule is useful during combustion because it provides for a more efficient burn. The net result is that less CO is produced because there is more oxygen to produce CO2. Interestingly, the total amount of CO2 produced is lower than that produced when petrodiesel is burned. The second chemical difference between petro and diesel deals with degradation, or biodiesel is degradable. The ester group makes it possible for biodiesel to be taken up by microorganisms and degraded. It also allows biodiesel to degrade through process such as exposure to light, and it means the biodiesel spontaneously degrades at a set rate over time. This is good when the fuel is spilled, but can cause problems during long-term storage. The third difference, and one that is a problem with biodiesel, is that the oxygen atoms make the molecule polar. That simply means that the end of the molecule near the oxygen has a negative charge, and the end farthest from it has a net positive charge. In petrodiesel, there is no charge, and the entire molecule is neutral. The problem with having polarity is that it makes it easier for the molecule to form into a crystal structure. In other words, it makes it easier for the molecule to freeze, and that's because biodiesel freezes at a temperature as much as 25 degrees Celsius above that of petrodiesel. Thus, biodiesel is less sustainable for use in cold climates. The fourth chemical difference between petro and biodiesel has to do with corrosion. The polarity of biodiesel makes it more prone to react with materials around it. This is particularly true of metals like zinc, copper, tin, and lead. Thus, biodiesel can speed up the process of corrosion or rusting of these metals and decrease the lifespan of some engine components. In the same way, biodiesel is more reactive with molecules called elastomers. That's another one I have trouble with. Elastomers. We'll go with elastomers, which give rubber its flexibility and durability. When biodiesel damages elastomers, it makes rubber more brittle and causes it to crack. The result is to damage gaskets, fuel lines, and other engine connections that contain rubber. As a result of the last two differences, engines often have to be modified or built differently to handle biodiesel. This means that older diesel engines cannot handle biodiesel at all. Modern engines are often rated using terms like B2, B5, B20, and B100. Basically, this refers to how much biodiesel they can handle. Say a B5 can only tolerate fuels that are up to 5% biodiesel, while B100s can be completely runoff biodiesel. They have 100% tolerance for them. Now I'm going to go into ethanol versus butanol. Clearly, butanol is more similar to a gasoline than is ethanol. The problem is that producing butanol is more difficult and has not been reliably demonstrated on a large scale. Many organisms like yeast or even some types of algae produce ethanol as part of their normal chemistry. That is to say, a number of organisms produce ethanol, just like plants produce oxygen or humans produce carbon dioxide. Many organisms only need carbon dioxide and an energy source to produce ethanol. In the case of algae, only water, sunlight, and CO2 are needed. Thus, it is easy to produce ethanol. The problem with ethanol beyond energy density is that it's highly corrosive to the engine component, especially rubbers, and it also takes a great deal of energy to produce. Changing feedstock from corn to like jatropha or simply using algae can help to offset this energy input. But so far it seems like that more energy is needed to produce ethanol than is derived from it. Besides, algae are better at producing biodiesels. Butanol is less corrosive than ethanol, and because it takes about the same amount of energy to produce, it is more efficient in the long run. The problem with butanol production is that it's difficult to do on a large scale, like I said, but recently several companies have devised plans to produce butanol in large quantities and are moving forward with plans to make it a commercially viable fuel, like biodiesel. But ethanol and butanol are biodegradable, unlike biodiesel. Unlike biodiesel, they do not freeze at lower temperatures and are more stable during long-term storage. Thus, biofuels may offer better alternatives to gasoline in the long run than biodiesel offers compared to petrodiesel. And moving forward, an understanding biology is assisting in the production of biofuels. By genetically modifying organisms, some companies have been able to induce things like algae to produce fuel that is so close to gasoline that one can hardly tell the difference. If it is possible to complete this process without investing a great deal of energy from standard fuels and thus obtain most energy from sunlight, then the production of fuel in this manner can actually reduce carbon emissions. This occurs because more carbon is taken up to produce the fuel than is released when it is burned. This holy grail of biofuel production has yet to be obtained, but it is theoretically possible. And thank you guys so much for watching. That is all of my presentation. Sorry I didn't have any pictures or anything, but my camera only records my face. So there we go. Have a lovely rest of your day.